Okay, so let's get started with a new topic. In this lecture, we're going to talk about infinite series. We're going to give a brief introduction. We're going to maybe prove one theorem, and then probably stop the video recording. And then in the following two series of maybe 2-3 videos that I record, we're going to look at other theorems on infinite series and look at how we can apply these in certain scenarios. So as math majors, I know most of you are, you've probably encountered infinite series in Calculus 2, right? So Calculus 2, at the end of that course, you have say tests to test for convergence, and you apply them, but you don't really prove them. In this section, in this chapter, we're going to prove several of those tools that you would probably use in Calculus 2. So in order to do that, we need to really nail down the definition of what it means to be an infinite series. And the way that we can do this formally, other than just writing like a sum symbol and kind of notice a pattern, is that we can think of infinite series as sequences. And we know a lot about sequences by now. We know about the Bolzano-Weierstrass theorem. We know about monotone convergence. We know about Cauchy sequences. We know a lot about sequences, and we really can define infinite sums as sequences. So how can we do that? So let x be a sequence of real numbers. Then, so x equals to x of n, sequence of real numbers. The infinite series that can be generated by that sequence, so we're generating a series, is defined recursively as follows. So you can think of infinite series as recursive sequences in a very specific manner. Namely, the new term of your sequence is your old term plus this number, right? So you're always sort of adding what you added before. So I'll just explain on this example here. So we set S1 equal to X1, and then S2 is equal to S1 plus X2. We're always adding the previous term. So it's not exactly recursive, but it is a recursive type of thing. And by doing this, we generate a sequence of numbers. And that is a sequence which we can study, right? It just so happens to be that S1 is equal to X1, Sk minus 1 is equal to the k minus 1 terms of the sequence all summed up, and then we add k to it. So it is like we are summing, but in doing so, we're generating a sequence of numerical values, which we will call an infinite series. In particular, we use the notation, the limit of this sequence is equal to the sum of the terms. Now, is that going to converge? It depends. It depends on the sequence of what are called partial sums. So each Sn or Sk, each of those terms is a partial sum for this infinite series, which again is defined as that sequence of generated by that sequence. Okay. The Xn terms of this series, they're just called the terms. I said it out loud. So each Xn is a term of that infinite series. Okay, so it turns out that if we are comfortable with sequences of real numbers, then we should be able to extend all of this to the sums, which are in terms of sequences. I know I'm repeating myself, but I'm just really trying to emphasize that infinite series are sequences of partial sums. Okay, that's the main thing to take away. Maybe in your notes, infinite series are sequences of partial sums from some sequence of real numbers. That's the important thing I want to emphasize. So I think, as with any definition that you encounter, we should probably look at an example first. So what I think, where's my first example? Oh, geometric series. Okay, so maybe let's suppose we have a sequence X Yeah, let's do geometry. X sub n. And this sequence is not defined on the natural numbers, but 0 together with the natural numbers. So we introduce notation n is equal 0 to infinity. We can define, I'm used to the general case. Sorry about that. So x is equal to the sequence r to the power n equals 0 to infinity, where r is just some arbitrary real number. Okay. So then, what notation should I adopt? If you look in the textbook that we're using, there's several different ways to write the notation. I still haven't picked up the one that I favor the most, but maybe I'll use the classic notation that you're probably used to from calculus. And this, which is equal to 1 plus r squared dot plus r mini k plus dot. So then this is what's called a geometric sequence. Or not geometric sequence, but geometric series. An infinite geometric series. Okay. So for each choice of n, right, we get a term. And as n increases, we get a sequence, right? So notice that, let's just say that, and I'll make some more room here and say, maybe S0 is equal to the sum from n is equal 0 to 0 of Rn, and that's just equal to 1, right? And then S1 is the sum equals from 0 to 1 of Rn, which is equal to 1 plus R. Okay, and the subscripts for infinite series do not necessarily need to start at 1. I probably should have said that earlier. So for example, here the subscripts start at 0. Okay, and then there's 2, again, just to like emphasize what's happening here. Here we have our sequence. And this goes on forever. Okay? So this sequence here, so I'll just write it out. So if this is our sequence, then the limit of Sn is equal to this infinite series. Okay? And it would make sense that if this sequence converges to a number, that number is going to be the same as that sum, right? You agree, hopefully, that we're using our knowledge of sequences and where the sequence is going to tell us something about where the sum is going as we increase the indices of the partial sums. Make sense?
Yes.
Yeah.
So let's see now if we can determine if this converges to something, right? In order to do that, we need to maybe study the partial sums so that we can write it in terms of a sequence that's like useful for us, right? So for example, we should probably notice that Sn let's say 1 plus r squared plus dot 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 plus rn, okay? So we notice that each term of the sequence looks like this, right? So there's an annoying trick. Well, it seems annoying because it kind of seems arbitrary, but if you tried to rewrite this in terms of something that was easy to evaluate at a limit, and you kept on like playing with it algebraically, you possibly would come up with doing this yourself. What I'm going to do is I'm going to notice that if this equals this, then r times Sn is equal to r plus r squared plus r cubed plus dot 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 plus rn plus 1. Right? If I just multiply both sides of this equation by r, I get this, right? Now, what I'm going to do is I'm going to subtract this sequence from this, not sequence, I'm going to subtract this sum from this sum. Okay, so if I just like subtract, I'll write it like long division looking. If I subtract this from this, what do I get? I get that Sn minus r times Sn is equal to, well, notice r minus r squared minus r squared, r cubed minus r cubed, rn minus rn, all the way through. The only terms that are left over are the 1 and the r to the power n plus 1. Which up here says that Sn times 1 minus r is equal to 1 plus r to the power n plus 1. Hopefully you can read that. Okay. So far so good. If that's equal to that, which it is, I know that this is equal to that, so I subtract this from there and I get this equation, which leads to this equation, which leads to the nth partial sum being equal to, say, 1 over 1 minus r times 1 plus r to the power n plus 1. Make sure you can read that. Okay. Just divide both sides by 1 minus r. And again, we're assuming r is not equal to 1 in order to do this, because you have to be careful. Whenever you divide, make sure that, so up here we probably say r is not equal to 1, because then we'd have a problem there. So now if the terms of if the partial terms are determined by this is our sequence, right? That's our infinite series, right? So what happens when we look at the limit? Well, I'm going to go ahead and like distribute this in, right? And just write this as, well, there's no n term here for 1 over 1 minus r times that. So it's just 1 over 1 minus r plus 1 over 1 minus r times the limit of r to the n plus 1 power. Make sure you can read that. That says r n plus 1 right there. I hate that it's so small looking. Fix that. Yeah. And so if I take the limit on both sides, I get this here. Now notice that the convergence of this sequence here, or this series, is dependent on that limit right there only. So in particular, if the absolute value of r is less than 1, right? If we're looking at like a ratio like 1 over something or negative 1 over something, right? Then we know that this converges to 0, right? It goes to 0. So then if that goes to 0, then this limit is just equal to that. So we can immediately see that if the absolute value of r is strictly less than 1, then this limit is equal to that term because this is going to be 0. So we have an observation now for these infinite series. This infinite series converges to 1 divided by 1 minus r, provided the absolute value of r is less than 1. Basically, it's in the open interval between -1 and 1, right? And again, as I just explained, because that ensures that that goes to 0, which means that this converges, and what's left over is that, so that's the limit. But what about the other direction, right? Like, well, not the other direction. What about, are there any other cases where this might converge? Where this infinite series might converge? Well, yes, we're going to address that in a moment, but first I'm going to pause the video. I'm going to erase this, and then we're going to prove a short theorem, and then look at what happens when that hypothesis isn't satisfied. Okay, we're back. So we just argued why this geometric series converges whenever the absolute value of the ratio r is less than 1. So we have the results here, that infinite sum actually converges to this formula. But what about when the ratio doesn't satisfy that hypothesis? What about, are there any other cases where that might converge? So something that will help us address this problem will be this theorem, which states that if the infinite series converges, then the sequence of terms equals 0. The limit of the sequence of the terms equals 0. Again, those are the terms, those are not the partial sums. Okay? So this proof is actually relatively simple. Right? So we can say something like, suppose that this infinite series converges. Okay? So that is maybe the limit of the partial sums exists. Okay, so that's how we've defined convergence. The infinite series converges if these partial sums converge to some number. Okay. Next, observe that the nth term is equal to the previous term plus xn. Okay, which implies that xn is equal to Sn minus Sn minus 1. Hence, if we take the limit as n goes to infinity on both sides of this equation, that this exists, right? This limit and this limit exist, and they also equal each other. So that means that the limit of the terms must equal 0. Done. Okay. Now, it's important to notice, to pay attention to the hypothesis and the conclusion of this theorem. This states that if the series converges, then the limit of the terms equals 0. It says nothing about the limit of the terms equals 0, implying anything about the convergence of the series. So I've noticed in the past that students mix that up. It's if this, then that, not if that, then that. Okay. But the contrapositive is true. So as a consequence of this theorem, we get that if the limit of xn does not equal 0, then the series does not converge. Okay. And that's just taking the contrapositive of that of the original statement. Okay. Now, this contrapositive of this tells us more about this geometric series. We know that the terms look like this. So when we take the limit here, right? Oh, no, we don't even need to consider that, right? So for the geometric series, we're looking at I is equal to 0 to infinity of R to the n, right? So here, the terms look like that. So if R, so this diverges whenever R is not in the interval -1 to 1. In other words, if the absolute value is not less than 1. So we have a larger statement here as a consequence of this theorem. If R is less than 1, then this infinite series equals that. If the absolute value of R is greater than or equal to 1, then the limit of the terms is not equal to 0, which implies that the infinite series diverges. Okay? So I think that'll be it for today's recording. So I'm going to go ahead and stop the video now.